So hey, I'm Professor Matt Turner with Electrical and Computer Engineering Technologies program at Purdue University, and you're watching another video lecture series for ECET 273 Modern Energy Systems. We've now moved on to loads, so this video is part one of two in a two-part series on the end loads, the devices that we connect up to the electric grid. Devices that use electricity to do useful work. So we're going to start quantifying those from kind of an engineering perspective. You'll notice that the title is actually the physical network loads. The next three modules are all going to deal with some sort of physical equipment that's connected to the electric power system. So right now we're just going to look at the ones that are in factories and homes and things like that that use electricity loads. We'll then move on to generators, and then we'll look at the transmission and distribution system. But for the next two classes, we're just going to be looking at these load devices, light bulbs and motors and things like that. So far we've been using the term load just really to simply refer to any device in a circuit in which power is being delivered, right? Anything that we connect to the output terminals of a voltage source, we've been calling a load. Well, in concepts of the electric power system, the term load has a much more rich and full connotation, and we're going to develop a much more specific vocabulary throughout today to really define what we mean by the word load. And how we're going to start is kind of where we left off previously with the concept of impedance. From an engineering perspective, we really look at loads in terms of their impedance Z, right? Which is the combination of their resistance and their reactance, and Z is often given as a formula R plus JX. R being the resistive portion of the impedance and X being the reactive portion of the impedance. You could also write this, recall, as the magnitude of Z at some angle. Just a conversion from rectangular to polar form. We're going to often use phasor diagrams to disaggregate the resistive and the reactive components of the impedance in real circuits. The technique of phasor diagrams enables us to look at how the different components of the load, how the R component and the X component of the load are going to affect the current flow and therefore the voltage drops in the circuit. So it's kind of a graphical technique to look at impedance, voltage, and current in a circuit. So in this figure here, we've got an AC voltage source which represents the connection to the utility system, and it's connected to a load that has a series reactance, a generic series reactance of X, and a generic resistance of R. Since this AC current, which we call I here, is flowing in the circuit, the inductor, which really is just representing the inductance of the load, is going to cause a voltage drop of IX, and the resistor, which represents the resistance of the lumped resistance of the load, is going to cause a voltage drop of IR. So we can say that there are two voltage drops in the load. There's one due to the reactive portion and one due to the resistive portion. Additionally, owing to the reactive portion of the load, there's going to be a phase shift between the voltage and current waveforms in this circuit. This is best, really, the relationship of all these voltages and currents is best understood in context of the phasor diagram. Before we get into actually drawing the phasor diagram, which we show here on the right side, I want to make a few observations. Across resistors, voltages and current phasors point in the same direction because current and voltage in a resistive device are always in phase. So that means since they have the same phase shift, the voltage and the current do with respect to the reference in a resistor, the phasors have to kind of lie on top of each other. They point in the same direction. Don't have to have the same magnitude, but they have to point in the same direction. Across the inductor, it's not the case. The voltage and current phasors in an inductor must be 90 degrees out of phase. And we know that because we say that the current lags the voltage in an inductor, and we know that that's a 90-degree lag. There's 90 degrees of phase shift between the voltage and current there, and it's lagging. One last thing to note is that because in this circuit, this is just a circuit analysis, in this circuit the components are in series, therefore the current through them must be exactly the same, including both the magnitude and the phase angle. So the current flowing, the current I here is the same as here in terms of both its magnitude and its phase. So let's use that information to construct a phasor diagram for the series combination shown here. So first in the phasor diagram, we draw the source voltage. And we represent its phase angle as 0, meaning that the voltage is going to point purely in the real direction. The magnitude of this vector represents typically the RMS value of the voltage sinusoid. It has a phase angle of 0 because we've chosen to use the source voltage here as our reference phasor. So on this phasor diagram, that's this right here, Vs, right? Vs and Vs. Its magnitude, the length of this vector, corresponds to typically to the RMS voltage of this, and it is drawn along the real axis because it has no phase shift. The next thing we're going to do is we know that there's this current that's flowing in the circuit. And we're going to just draw a generic current vector representing this, and we're going to draw it in the fourth quadrant. So I'm just going to draw this little current element right here. It's in the fourth quadrant of the IR plane. So I want to just kind of say that this graphical choice is only partially arbitrary. While I don't know yet the exact theta, because I don't have actual values for R and X, I do know that it has to fall in the fourth quadrant because this is an inductive element. Current lags voltage in an inductive element, so therefore it falls into the fourth quadrant, right? Current lags the voltage in this inductor. The magnitude of the phase angle of the magnitude and the phase angle of this current would actually have to be calculated based on the values of L, of R, and of course the frequency. But suffice it to say that this is a generalized representation of an RL load. It's a generic RL load. So now let's apply circuit analysis to this. From Kirchhoff's voltage law, we know that the voltage drop across the reactive element and across the resistive element must add up to equal that of the voltage source. So if we were to write that out, we've got Vs equals IR plus Ix, right? In phasor form, there's an additional requirement that the phase of Ix and the phase of IR must also add to equal that of the voltage source, which in this case is 0. So we can therefore use that information to kind of graphically decompose the source voltage into a component that is collinear with the current, representing the drop of IR across the resistor, and one that is perpendicular to the current vector, representing the drop of Ix across the inductor. So what we're saying there is that the voltage drop across the resistor has to be in phase with the current flowing through it. We know its magnitude is given by the magnitude of I times R. So what that is saying is we're drawing this vector right here. It points in the same direction as the current vector, and its magnitude is equal to IR. So that's really just, we would say that's VR, right? That's the voltage drop across the resistor. We also have the perpendicular element, right? We know that the voltage across this reactive element has to lead the inductor by 90 degrees. So if the current through the inductor is this element here, we need to rotate 90 degrees. Right? That's that element right there. The magnitude of it, of course, is dependent on the reactance. The angle theta here that we drew is determined by the relative magnitude of R and X, and it comes from the solution to this equation right here. In this way, we see that the voltage across the inductor leads the reference voltage, the voltage across the resistor lags the reference voltage, and the current through both of the devices lags the reference voltage phasor. So now we've drawn this phasor diagram, right? Here's the reference. Current through both lags the reference. Voltage across the resistor lags the reference. Voltage across the inductor leads the reference, right? So that's a complete phasor diagram, really showing Kirchhoff's voltage law for this simple circuit. It's a very powerful technique that we'll use a lot in this course.